The following is a recording of a webinar on pole fire mitigation by John Laletta, the Chief Technical Officer at Exactor. This hour-long presentation will explain the science of how pole fires get started and discusses the strategies your utility can use to reduce pole fires.
Well, good afternoon, everyone, and thank you for joining us today for this informative webinar. I'm Mike Mazingo of Hometown Connections, and I'm excited to introduce you to our speaker today. John Laletta is the Chief Technical Officer for Exactor, Hometown's trusted partner for utility system infrastructure risk management. John has agreed to speak with us today on the issue of pole fires. We will learn from John how these fires originate and what measures we can take to reduce the likelihood of fires. He'll also run us through a case study where his company, Exactor, was able to assist a utility with alleviating this problem. You will have an opportunity to ask questions at the end of John's presentation. Again, thank you for joining us. And also let you know that a recording of this presentation will be posted on our Hometown Connections YouTube channel. And we'd love to hear from you how you heard about this webinar. So without further ado, John, I'll turn it on over to you to make the presentation.
Thank you, Mike. Welcome, everyone. This is a very important topic that we're seeing more focus on throughout the industry as climate change has an impact on the environment our systems work in, and the impacts of pole fires and wildfires are becoming a very topical element of news broadcasts anymore. So it's something to avoid. And so what we want to do today is look at not only the statistics surrounding pole fires, and as Mike said, we'll cover a case study at the end, but what causes a pole fire, and what are the mechanics behind the actual process that has to be followed for this pole fire event to happen. So, of course, there are pole fires that occur when lightning strikes that happen, things like that, and vandalism. But what we're talking about here are the naturally occurring pole fires that are associated just with normal operations and the wear and tear of the electric grid that we all have to put up with. And of course, environmental change has an impact on this whole process. So we're going to go through some laboratory evaluations of how pole fires begin, what are the warning signals that teach us how to avoid the pole fire problem, and then strategies to mitigate pole fires if you find that on your system there are areas that are prone to pole fires. So we'll begin with just the idea that in fact pole fires just happen, and a lot of people say that it just one of these things that you can't avoid. It just they're there, but that's not quite true. The pole fire that occurs from normal operation and wear and tear of the grid, they happen because of a number of elements that occur prior to the actual event. And pole fire may take a year to develop before it actually comes to the fruition where there's wood flaming or brush below the pole catching fire. So we'll look at all of this and see if we can't learn how this process begins and what we can do about it. What was surprising to me as I started studying this topic was that it's not pole fires are not typically caused by major equipment like transformer explosions or fires or capacitor explosions, but really they're caused by a lot of normal events that we're going to look at that occur every day across your system. We've looked at pole fires from a historical standpoint, and typically you would say that a pole fire itself will generally cause collateral damage. And that's a very expensive proposition for any electric utility because it means that you have to be involved with public relations, maybe litigation, and so on as a result of the event occurring. They certainly create hazardous work environments because now you've got your linemen in a bad situation. You've got firemen involved who aren't as adept at working around electrical situations, particularly when the conductors are live. And the final thing is that in our studies, we've documented that pole fires are increasing. And there's a number of factors that feed into that frequency of pole fire occurrence. So what I've been doing is for the last several years, actually about 6 years now, 6.5 years, I started my own non-scientific study of reports of pole fires. Now, this is like from a clipping service using Google. And when they see headlines that include the words pole and fire or power line and fire or electric line and fire, they send me a clipping of the news alert that's associated with that. So in this period of about 6.5 years, I've accumulated over 12,000 reports of pole fire events. Now, they're not all unique, but there are about in that 12,000, about a third of them are unique reports because a number of reports get reported by a number of news agencies. And as I study these reports, I found 9 common causes cited as the reason why the pole caught fire. And these are them. And some of them, there's not a whole lot we can do about it. A car accident, for instance, there's not a lot you can do about that. But the others are sometimes involved with things the utility is working on, like animal control and vegetation and so on. But look at this one area, the gray and the orange, the spontaneous, which is just where a fire erupts from the pole itself and down power lines. And that could be a power line that falls off an insulator and lays on the crossarm and causes a fire, or one that hits the ground and causes a fire there that involves the pole. So those are a couple areas that we can really look at and try to do something about. So what are the avoidable causes of pole fires? Well, broken insulators, loose ties, broken crossarms, mechanical failures on the pole itself. And then there's the spontaneous combustion events, which are generally associated with cracked insulators, contaminated insulators, and high leakage currents that result from those events. So we're going to focus in on those 2 areas today because these are areas that you could do something about. You could avoid all of these areas if you use predictive maintenance strategies within your utility to find problems and eliminate them from the pole or from the line or from the circuit prior to collateral damage occurring, like a pole fire, and then the further collateral damage that results from that pole fire. So we were in 2016, we were asked to assist Seagray, which is if you don't know Seagray, they're an international electrical engineering organization, much like IEEE. And we're in a working group on wildfires with them. And pole fires are a big part of wildfires and becoming a bigger part because as pole fires increase, more brush fires result, more wildfires take off. So we were asked to do a survey in the United States, and we sent it out to, I'm going to say 300 or 400 utilities, and about 70 of them responded and helped us with our results. And then this survey was incorporated into an international review at Seagray, and then they published some papers on the statistics associated with pole fires, wildfires, brush fires, and so on. So we ask our survey participants several questions. I'm just going to cover a few of them that I think are germane to our discussion today. So we first asked, have you had coal fires in the last 12 months? And over 2/3 of the utilities that participated in the survey said, yes, we have. So that's a big number for anything. And 20% said, no, we don't really get coal fires. We asked, did the coal fires lead to brush or house fires associated with the event? While most utilities, 2/3 of them, said no, an astounding number said yes. So 26% of the people that answered that question agreed that collateral damage is a problem in their area. And of course, this is going to be kind of a regional result across the country because different areas have different problems associated with the number of pole fires as well as damage associated with them, whether they're rural utilities or urban utilities, things like that. We asked what the most prevalent cause for the pole fires were, and we got a variety of answers. Nothing really stands out other than aged infrastructure and equipment partial discharge. And of course, Exactor uses partial discharge in our analysis of the grid, looking for deteriorated equipment. So this fits right in our wheelhouse with these other things. And we were surprised that weather conditions were only 20% of the pole fire events. So when you look at that, about half of pole fires were caused either by aged infrastructure or deteriorating electrical equipment that would allow problems associated with high leakage currents to be participating in the pole fire problem. And we'll get into more of that in just a moment. We asked, would you say that more fires are prevalent on distribution or transmission? Well, there's a whole lot more distribution poles, right? There's 160 million to 200 million distribution poles in the United States alone. So you would expect that to be the bigger number. And transmission structures are usually relegated to the lower voltages, 230 kV and below, for transmission that would participate in a pole fire. So that kind of makes sense in the distribution of that work. But it does also say that there's a lot to do on the distribution system to eliminate those fires. We asked the participants, when do you have pole fire problems? And I can tell you from our customer standpoint, they tell us the spring is the worst time where most fires are prevalent. It follows, of course, the winter salting of roads and a lot of contamination issues. But in the survey, it was pretty much split between summer and spring. And then a big portion said they didn't see any correlation to the time of year. It just they pop up. And then we asked a question regarding the type of weather that was prevalent during the period pole fires were experienced. And you can see that dry to wet conditions were a big area. The winter to spring transitions, which our customers seem to tell us a lot about, and then extremely dry periods. And as we're seeing right now, at a topical point on the West Coast, dry conditions are causing fires of all sorts to be across the West Coast and in the Plain States as well. And an interesting issue associated with that is that the contaminants that are put into the air from a wildfire contaminate your insulators and lead to pole fires themselves. So, and we'll see how that occurs, but isn't that interesting that we have a circular set of events here? A pole may participate in the production of a wildfire. The wildfire may participate in the production of contaminants, and contaminated insulators, which lead to pole fires. So it's almost a circular problem that may be driving the increased frequency of pole fires. But here's the real zinger that I felt in this whole study. We asked the participants, do you have a mitigation program? And more than half of them said no. 16% said not sure. So I guess you could say that's a no as well. So, 3/4 of the utilities couldn't provide us with a mitigation program or strategy at their utility to avoid this problem. And the sad thing is, this is a real avoidable problem. Just like there are other avoidable issues with vegetation management, you can reduce or eliminate vegetation outages and so on by proper management of the trees and bushes. But with pole fires, not so much. So I'm part of a number of IEEE working groups and study groups. And in IEEE 454, partial discharge is categorized into 4 specific areas. And partial discharge is an important topic to understand when we're talking about pole fires, because as you remember, deteriorated equipment was a large contributor to a pole fire situation. So when partial discharge exists, it exists because there is a deterioration of the equipment in some form that we'll look at in a little bit. But the number one area was internal PD, such as voids within materials. There's been recalls over the years on cutouts that were mismanufactured in the porcelain, lightning arresters that had voids in the MOV materials and so on. And those voids allow a partial discharge signal to develop. Surface PD, where there's the material on the surface of a insulator, as an example, has become damaged or contaminated, and it goes into what they call dry band arcing as a precursor for high leakage currents that contribute to pole fire issues. Corona PD is one that we don't use in our evaluation of deteriorated equipment because it's so influenced by humidity. And most of our work is at 34.5 kV and below anyway, because we're working with distribution utilities in most of our deployments. And there's really no corona at that level and below. But when you do have corona as an indicator of partial discharge, got to be very careful, because it can simply be high humidity that's causing that corona to be developed. And then any kind of floating conductor or component, something that's broken loose and is, instead of being bolted on, say like on the top of a lightning arrestor, it's just laying there, making a connection, not a good connection, and a high impedance connection, but nonetheless a connection is made. And of course that high impedance connection is going to go into partial discharge. But what we really like is the surface PD issue, because it's a perfect one to mitigate pole fires by detecting and analyzing, locating the source, and then mitigating the problem. And to do that, you have to be able to receive the emission, which is a VHF kind of RF signal that comes from partial discharge, but you also have to be able to understand the signal you're listening to, and you have to have a way to locate that emission source. So we do that by we've developed signatures for partial discharge, and those signatures are very specific emission characteristics. So it's not just, we're not just listening to RF that's being transmitted from some source, but we're listening to exactly the the emission that comes from a piece of deteriorated equipment. And if it's surface PD that we're listening to, that's a precursor to further damage to the pole that we'll investigate here. So this is just a lucky event for us that we can help utilities eliminate pole fires by our standard partial discharge characteristic signature emissions and the way we study those, the way we locate the source of those for our customers so that they can go right to that pole and either clean or change out that insulator before it contaminates the pole with a high leakage current. So everything has a leakage current. We all know that. It's because of the AC nature of the system. We're really just above ground. We're not away from ground. So there's always currents flowing down the pole from the energized equipment, but it's usually less than a few milliamps, and it's very capacitive in nature. So it's something that when you look at it and measure it, if you have a grounded pole and can look at the ground wire itself, you'll always find some leakage current from the system above. And in high humidity times, that leakage current may go up a little bit. But when it stays low and capacitive, the poles seem to withstand that pretty well. But when there's surface PD, and coming from contamination, cracks in the insulators, dry band arcing, which we'll explain. When that happens, the current now, it blooms and it can get up to 500 milliamps, and it's resistive in nature. And it flows around and through the wood of the pole, and it collects at the metallic points on the pole, like at the king bolts or brace bolts on your pole. And that's where we really get into the problem of charring. I'm sure you've seen that when someone has said this, the cross arm smoking, and you've taken it down. You can see right where those bolts go through the cross arm. That's where the charcoal is beginning to form and the problem is beginning to develop. In papers that I've studied from IEEE and other sources, it looks like continuous currents of around 10 milliamps or even less can, over time, bring a pole to the pole fire situation. So how does the process run? Well, something happens to the insulator and we get into this resistive current flow. It could be contaminants that fall onto the insulator. And then it's not just the contaminant, but fog and moisture, dew, rain, combined with that contaminant on the surface of the insulator. And when that happens, you get very specific current flow on the surface of the insulator, and a race begins. Either the rain or the dew washes off the contaminant before it gets into a problem, or the contaminant, the moist contaminant, the water boils off and evaporates. And now you've got not just a contaminant, but you've got a contaminant that is not going to wash off the insulator. You either have to change the insulator or you can use various techniques, but it's on there. It's not going to casually be washed off. So that's when you get these dry bands beginning to form. And that's what we want to avoid. Now, the good thing is when the dry bands form, they cause this process called scintillation. And scintillation simply means give off light. And I've talked with utilities who will take two linemen in a car, and one will drive and one will hang his head out the window at night and look at the insulators as they drive down the road and look for that blue glow that comes from a very severely contaminated insulator for a changeout program. That's kind of a resource laden and probably not a real safe way to do this work, but it's the same work being done. They're looking for an insulator that has these dry bands associated with it. luckily for our customers, we can pick that up with our sensors. And because we know the signature of that signal, we can pinpoint exactly where on the grid that emission source is as the vehicle that we have our sensor in is driving down the road. And that vehicle could be a car, a truck, a fleet vehicle, could be a helicopter on transmission work, or a drone. But the combination of energy content measurement of that digital signature rather, and the motion of the vehicle allows us to pinpoint exactly where the source of that emission is for action by the utility. Now, I mentioned that the metallic components on the pole are really where the problem is going to center itself. And of course, it's the lowest impedance part of the system, right? So the currents collect, if you will, at the king bolt. And when the king bolt gets warm, it accelerates the drying out of the cross arm at that point. And now you get partial discharge from that interface between the wood and the bolt that's no longer tight. It's now loose because the wood is shrinking away from the bolt. And it continues to deteriorate right there. And that's often the source of the pole fire initiation. That you'll see embers that will pop out from that area. If a gust of wind comes along, it may ignite the area and start the pole fire, actually. But the big problem that you want to avoid are these embers popping off, hitting the ground like a cigarette butt, and starting a fire on the ground. And of course, dry weather, like in the western half of the United States, contributes to this problem, and it exacerbates it. This study was interesting just because it calls out the fact that contaminated insulators that are in this process of scintillation. So they're contaminated not just casually, but actively, and are participating in the pole fire process, really are a problem for a number of reasons. Because now this insulator has been damaged in its ability to insulate the wire from the ground or from the pole. And it's like reducing its BIL, basically. And it's because these dry bands on the insulator itself are not as insulating as the normal glaze of the insulator itself. So the insulator, as it collects these dry bands, these little pockets of heated on contamination, begin to deteriorate the function of the insulator itself. And now that insulator is going to be the one that flashes over during a transient event like a switching surge or a lightning surge. And when the lineman goes out and the circuit's dead and he doesn't see any dead animals laying on the ground, there's no trees touching the wire, he comes to the point of, I don't know what's wrong, and he'll slam a fuse in or reclose an operating switch, and everything holds. Well, that's because the flashover burnt off those dry bands from the high energy event on that insulator, and that resulted in the insulator kind of going back to more of its normal condition and holding. So now you don't know where the problem is, and the lineman will mark, unknown cause of the trip. Well, the issue here is that event, that high energy event, has damaged the surface of the insulator and its hydrophobicity. So now it's going to be more apt to collect dry bands again. So this is a problem that's going to recreate itself over and over again, and it's not gone. It just temporarily healed itself, if you will. So the dry band, we've talked a little bit about it. It's something you can't see typically. We looked at it in the laboratory in a number of ways, and the issue is you can find it with the emission of these very specific RF signatures. And by knowing how to listen for those, you can locate the source of that. And it's been studied in laboratories to the point where you can calculate statistically how many dry bands on an insulator will lead to that insulator flashing over. So there's kind of a threshold of the number of dry bands on a surface of an insulator. So scintillation will eventually lead to a flashover. We've talked about the currents, how they move from capacitive to resistive, how they increase during this period of scintillation. And if the number of scintillations on an insulator across a number of critical number of them, a flashover is going to occur. So this is, you can't see this very well, but here I outlined it, is an insulator in a laboratory setting. It's in the dark, so we can see the scintillation actually occurring. And there's a source of the failure signature emission, that little blue light underneath one of the dishes of the insulator itself. The dry bands themselves, we add to the insulator to demonstrate the problem of collecting dry bands and the impact that has on the operation of the insulator. And as we add these dry bands, the insulator itself begins to create streamers. These are not a flashover yet. These are arcs jumping from point to point on the insulator itself. Mike, I saw someone's hand go up. Is there a question? You're on mute,
Yes,
Mike.
that was me asking a question.
Oh, okay.
Where would you look typically in a town or city that you find the most contamination on insulators? I know maybe we had a conversation a few months ago, and you pointed out that airports are a location where you've got particulate coming from jet engine exhaust and it collects on insulators. Are there other areas within a community where you might expect to find a higher level of contamination on insulators, maybe associated with a manufacturing facility or some other location where you might look first for contamination?
Yeah, well, you hit one. Industrial plants that have exhaust of one kind or another. Cement block factories, for instance, they are really known for this problem. Farm agricultural installations like chicken farms and places like that have a lot of dust in the air that gets out isn't well controlled. Roadside poles, which most poles are, at higher speed areas like on highways, you get a lot of road contamination, carbon black from tires and so on, eroding. And anywhere where salt sprays or salted roads exist during the winter, excuse me, that results in salt air getting up into the overhead. So it's really anywhere, unfortunately, and dust where it's dry. And as I mentioned earlier, we had on the East Coast, we had dust from wildfires in Nebraska a few weeks ago. So we could see it in the air. The air turned yellow. So things like that carry the contaminants along. So really, it's almost anywhere. And again, that's probably why we're seeing a higher incidence of pole fires in general.
Okay, thank you.
And then the next thing that happens, of course, after the streamers on an insulator become active, a flashover occurs. And then the high energy event that follows damages that whole area of that insulator. So it's going to be more likely to pick up problems. So in all of what we've gone through, here are the conditions that are the generalized ones that lead to pole fires. very dry drought conditions, followed by moisture. Wet, light rain leaves the wood less resistant to leakage current. So anytime there's a rain event, you have the issue of how well the wood is going to participate in the insulating of the system because of the penetration of the water into the wood. There seems to be two high risk periods for pole fires. The first half hour after a rain event, which would which would fall back to that wetness statement, and then during the first hour after the rain event occurs. So we have those two areas that seem to be the most prevalent time for the onset of a pole fire. The end of a dry season, which follows right along with those ideas, as a whole, is a element that participates in the contribution to this problem. And then high leakage currents being produced during high humidity, where the humidity is greater than 70%. So if you live in an area with high humidity, that you're going to have more associated pole fires than places that are very dry. The other thing that is very important to understand is as the poles themselves dry out, they become more apt to be participating in a fire. And it seems to be something on the order of 35 years or older is when poles really begin to be associated with contributing to the pole fire problem itself. So we talked about some of the issues associated with the ignition of a pole fire, wood shrinkage and crackage, the age of the pole, the wetness of the wood, and the moisture of wood accelerating the burning points at the highest electrical field areas on the pole itself. So how do we mitigate this? Well, we talked and demonstrated that when you get into the problems leading to a pole fire, you get this delightful partial discharge emission. And if you know how to listen for it, and you know how to evaluate the source of that, you get a free sensor basically on your system alerting you to the problem. And so now you can do something about that. We look at pole fires as taking about 3 or 4 months from the onset of leakage currents to the event occurring. And the event occurring may come at those high humidity times or wet times, but it's been going on for some time. And you'll see that when you take the pole apart, if you can, if it's not burnt completely, you can see where at the bolts there's charcoal just basically building up as the pole begins to participate in the process. Bonding is a technique that some utilities use that can reduce damage. But however, bonding raises the ground to the top of the pole. So now you've got a higher stress at just the top of the pole. So you don't have the benefit of that riser from the ground up to the crossarm as part of the impedance of the system to minimize the serial impedance or maximize the serial impedance or minimize the serial current flow through it. So I don't know. It's it's sometimes some people swear by bonding, others avoid it. And then replacing metallic parts with fiberglass parts, it may help. We don't know. We're not, we don't sell those things or recommend them, but we see more and more people using fiberglass components rather than metallic components in assembly of poles. And the thing to remember is that you can't just hope for, because we had a big rainstorm, the problem's now gone. Because these dry bands are sticky. They're stuck onto the surface. They're baked on basically to the surface when the heat from the axial currents causes that moisture to evaporate and bake it right on. Kind of like when you leave coffee in your coffee cup on Friday and you come back to work Monday and there's a crust in the bottom of the cup from where that evaporation has occurred. You have to really scrub that out to get rid of it. And that's exactly the situation you got with a dry band. Polymer insulators are better, but they themselves over the decades of use have gotten better. So the older polymer insulators may contribute to this problem more than newer ones. So it's just, again, you don't have to worry about it if you detect the problem by listening for these partial discharge signatures, because they'll be there regardless of the material that the insulating materials are used. Now, across the country, we have data from utilities all across the country, and we've broken that into 6 regions so that we can kind of know what to expect when we go into a study area. And pin insulators are the #1 problem for electric utilities from a deteriorated equipment standpoint, but it's also the #1 item on your system, right? You have more of them than anything else. And luckily, they're easy to change, usually can be done hot. But if you look across the country, you can see that pin insulators contribute to deteriorated equipment findings in different ways in different regions. And the worst is the Northeast. And we assume that's because of the freeze-thaw cycles that they go through and the high wind events that occur during these environmental times. So the way we would approach a problem would be to be called in to a utility where problems exist, and we would put our sensor in vehicles and drive around the circuits. And this is shows a survey that was done at an actual utility, and you can see the white lines. They're where the survey vehicle ran. We're listening to VHF radio emissions, so it doesn't matter how fast the vehicle is traveling. It just travels at posted speed limits and so on. And then every time the signature of a partial discharge occurs and is detected, the sensor marks the location using GPS technology. And you can see there's a lot of problems here, 1,000. Well, that doesn't mean much because there's a lot of transient events associated with the detection of partial discharge. Partial discharge can travel down the conductor, and it appears to be at the next pole as well, when it really isn't there. It's more of an echo of a partial discharge event somewhere else. So our secondary analysis eliminates those partial discharge phantoms and partial discharge transients, and leaves us just with, out of that 1,000 readings, 25 places on this grid, probably about 100 miles or so, that have an insulator at these points or more, maybe more than one insulator or device that should be replaced to eliminate the problem. So it's a very pinpointed, accurate study that's run and provides you with very good efficacy in the results. So throughout our history as a company, almost 18 years, we've kept a KPI internally that is when we say there's a problem, do we find a problem? And that efficacy is higher than 99.5%. So we've managed to, through years of study, research, and development, optimize our algorithms to the point where we tell you there's a problem, go fix it. And you'll eliminate either a pole fire or a potential circuit outage that can be predictively eliminated. So, Mike, we didn't test this. I apologize. So I'm going to ask you, Mike, if you just raise your hand if you can hear the sound. If not, I'll have to reshare the presentation. Do you hear any music?
Sometimes utilities will notice insulators that are.
Let me, I'm going to have to stop my share just for a moment and then reshare in a different way. That wasn't what I needed.
I can actually hear the narrator there for a second.
Could you?
Mm-hmm.
Let's see. It says share sound, but
Okay.
let's try it and see what happens.
Yeah, let's try it again.
Sometimes utilities will notice insulators that are
I can
seriously
hear.
damaged,
Okay.
even melted down. Professor Sibo shares on this.
That if the protection is not quick enough and the flashover is there, it could damage the insulator itself. And this is why you can see melted sections of the conductor tie wires, suspension insulator caps.
The heat factor of scintillating insulators is another issue. Leaking or arcing insulators are continuously releasing heat into the wood poles, which over time can cause pole fires, broken poles, and create significant line and circuit damage.
So what we did in these studies, this is 2 parts of a 6-part series on our website that were laboratory investigations we did, and we put 2 insulators on 1 conductor on a cross arm, and we energized that to line voltage, and then we contaminated 1 insulator and left the other insulator clean. And we saw that the contaminated insulator in that video did have some arcing going on it. So let's look at it a little bit further down the test scenario, and you can watch this whole series of snippets of this laboratory study on our website at exactorinc.com.
The question is, how can you delay this process to keep the insulator cleaner? How can you do that? Uncontaminated, dry, clean insulator would not flash over because the operating voltage is much less than the flashover voltage of the insulator, much less than the withstand voltage of the insulator.
But what if you could pinpoint the specific insulators on your system that were most likely to flash over?
So if you have any instrument, any system that would be able to detect this type of activity, then the distribution line is still in service, that would be valuable because then it is not an outage type of problem that you have, but it is a prevention type of problem that you have. I'm not a utility engineer, but I would say that if I would be one, then I would look for a meter that would show which are the active insulators.
So what determines an active insulator?
Where you have scintillation, partial discharges, dry band arcing on the insulator most of the time. So if an insulator is contaminated, not cleaned, rain was not able to wash it off, then you would have significant durations of time when the insulator is active. When it is drying out after rainy periods, then the insulator, which is close to that contamination flashover, would remain active. When it is completely dry, then you won't find these signs at all. As a general word, scintillation means that you produce a light or a pulse, and this shows how valuable a predictive type of instrumentation is, because in that case, you don't have to go up using a bucket truck after 9 p.m. and see what insulators are bad.
So Dr. Sibo was actually my lead professor in my graduate work at Ohio State University, and we hired him and his colleague, Dr. Caston, and the laboratory to do these studies throughout the history of our company. I see there's a chat, someone in chat. Oh, that's yet you, Mike. Okay. I thought maybe there was a question. So this is a case study. We did this with a municipal in the Western United States. We have never gotten the approval to use their name, but if you're very interested and call me or something, I'd be happy to give you more information. But this kind of gives the highlights of the study. They had this is a really interesting engineering study because as engineers, we seldom get a lot of good pre-problem data. We get problem data, but not what was going on before. And in this case, this utility recorded on a 200-mile stretch of their system 10 to 12 pole fires every year for the last decade. So they've had a history and they've tried everything they could think of, infrared studies, visual inspections, all sorts of things to try to figure out how to stop this problem. And they just couldn't get it stopped. And it was very specific on this 200 miles of line. So they called us in out of desperation more than anything. And so we took a look at it and we did our study. There was about 6,000 medium voltage poles in the study area. That represented about 30,000 pieces of equipment that could participate in this problem. And what we found was that only about 0.7% of the poles that we studied had a piece of deteriorated equipment that was indicated by partial discharge emission. And 0.2% of all the equipment was in a state that could contribute to a pole fire. So now we had it narrowed down to these few insulators out of the 30,000 devices, 0.2% of them were involved. And that represented about 65 devices themselves. So the utility changed out all 65 devices with brand new ones. And from that point forward, for 3.5 years now, they haven't had one pole fire in that 200 miles. So that's a real telling project with history, events, and then a change in the history to a new future for that utility. It's amazing, and that you can do that though everywhere. And what we learned was this 200 miles of line was near a very large airport. So it was probably, like Mike was mentioning earlier, contaminants from airplane engines that were going over the line as they took off and landed. So they're not going to change that. So now we got to figure out something better to do. And the better thing to do is to monitor the line for these partial discharge events, remove the equipment, and avoid the problem of pole fires altogether. Oh, I just say if you wanted to scan that QR code, you get a copy of this case study for your own. So how do you do this now? How do you actually take care of the problem? Well, you create analytics for planning. You find out where the problems are occurring, and you take direct action to locate the problems on your grid. This minimizes the maintenance expense because if you wait for the outage, it's the most expensive replacement program you can have. You need to pinpoint the deteriorated equipment, not just to this pole, but to that insulator on the field side of the bottom crossarm. That's the one problem area that you got to take care of. And this predictive strategy mitigates risk because now your linemen aren't working in an emergency situation. They're working when they have schedules, they know what they're going to do, and they can do it during daylight hours. You can mitigate the cause of pole fires, and of course, the pole fire itself can cause a lot of other costs and outage durations that you just don't want. At that utility we were working on, they said the average cost of a pole fire was $25,000. The average cost of changing an insulator on a schedule, $500. Much better deal. and you can reduce outages to your customers and the duration of those outages. So, the whole reduction of SAIDI and CAIDI is an important element in everybody's, excuse me, everybody's planning. And as I mentioned before, and I think the number one thing is we can improve worker safety. So predictive maintenance means change an insulator. The restoration plan means rebuild the pole. So I want to thank everybody for attending and for listening to our discussion. I'm happy to answer any questions. My contact information is at the bottom of the screen on that QR code, and that mitigation study is in the upper right-hand side of the string. You can screenshot it and scan those, or just scan them on your computer and get that information. So Mike, I'm going to turn it back over to you.
Okay, thank you, John. That was most informative. And for those who are joining us from out of town today, feel free to ask questions now, or I'm sure John would, if you come up with a question later, please email John and ask him. He'll be more than happy to respond. I did have one additional question, John, before we leave. I know that you've talked a lot about how pole fires can have collateral damage. Have you looked at what some of the liability for some of that collateral damage? I know some of the California utilities have gotten into a lot of trouble with wildfires. Not sure how they started, whether it was lightning strikes or failure of equipment. But have you guys, in working with utilities, kind of looked at, do you help yourself as a utility if you do this type of work predictively, that you reduce your insurance premiums, for instance, or have you been able to put a dollar figure on what some of the potential collateral damages, kind of an average that a utility can expect?
Well, if you remember, the largest utility in the country had a wildfire there in the upper or the West Coast and burnt down a whole city and killed a number of people. And that caused that utility to go into bankruptcy. And they're still fighting through that whole mess. That's the scary part of all this, right? Because if you hurt somebody, you just don't know what that liability represents. And it could be, we were at one utility, they were telling us that a capacitor on the pole blew up and oil came down on top of a car. And there was a lady in that car with a baby, and she sued the utility for putting the baby in a situation of being near cancer-causing materials. And whether they did or not, I don't know, but they were having to litigate this horrible lawsuit. And there's a number of deaths every year from fires that are shown to have been had poles and lines contributing to either the start of the fire or the continuation of the fire. So it's a real problem across the country, and it's getting worse. Everybody's getting more and more litigious in their work. And I don't know much about insurance with electric utilities, but I have talked with insurance companies who do insure the utilities for liability, and they say absolutely the maintenance of the equipment and the grid itself is a number one element when they look at the payments that the utility has to make for that insurance. So it's a win-win all the way around to use predictive technologies, whatever they are, to eliminate problems before they cause a problem. And to me, that number one is line worker safety. You put linemen in jeopardy every time you send them out on an emergency, particularly in the dark. And the number one problem for linemen is trips and falls. And that's the number one safety issue. And well, when you're walking a line looking up in the dark of night, it's a lot easier to trip and fall and hurt something than during daylight hours when you can have a normal situation and you're not looking for the problem. You're just going to the problem to solve it.
Right. Well, John, thanks again. Always a pleasure to hear what you have to share with us. I can see now why you're part of the Ohio State University Engineering Hall of Fame. You're just a wealth of knowledge, and hopefully our participants today found many things that they can go back to their team and talk about how to use this predictive maintenance to make things safer, more efficient, and save the utility a lot of heartache and trouble. So thanks again to everyone who joined us. And just a reminder, this will be posted on the Hometown Connections YouTube channel if you'd like to direct some of your friends and colleagues to it for their edification. We'd appreciate you send them our way. And once again, thanks to John Loletta and Exactor for putting together this wonderful presentation for us today. And have a great day, everyone, and enjoy your weekend.
Thank you, Mike. Thanks to all.
Thank you for watching this presentation of Hometown Connections. Please like and subscribe.